Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, Kobe and I chat with Muthu and Karmit from Ligero, sometimes also referred to as Ligero. We cover what inspired them to work on cryptography like MPC and ZK for almost 20 years, and how this space has developed since they started. We discuss Ligero, what led to the project, the early phases of the project, and the work that they're doing today. We return to the MPC and the headwork and discuss how they have improved on this system. We cover how MPC and ZK are interrelated, how their system incorporates the advances and new techniques from both fields, the new Ligetron system, and how they plan on getting this technology into the wild. Now, before we kick off, I just want to share an update about another project that I work on called ZK-Hack. ZK-Hack is a learning hub for all things ZK. Just over 10 days ago, we hosted ZK-Hack Krakow, which was so amazing and special. 40 projects were built at the hackathon, bringing the total number of ZK projects built at our ZK-Hack IRL hackathons to over 100. And we announced in the closing ceremony of that event that we have an upcoming event. That is ZK-Hack Montreal, which is bringing this event series to my hometown. ZK-Hack Montreal will be happening from August 9th through 11th, and it promises to be a very special one. Once again, we are hosting our ZK-focused IRL hackathon. This is the event you should join if you're looking to experiment with ZK tech and tools. It's also the first time that we bring our hackathon series to North America. And just as an aside, Montreal is also amazing in the summer. So if you've never been to Montreal, you should definitely check it out. We are just kicking off the development for this one, but wanted to give you a heads up. Applications are open, so yeah, I hope you'll join us. One last note, there's no episode next week. We are taking the week off, but we will be returning the week after with our regularly scheduled program. Now, Tanya will share a little bit about this week's sponsor.
Aleo is a new Layer 1 blockchain that achieves the programmability of Ethereum, the privacy of Zcash, and the scalability of a rollup. Driven by a mission for a truly secure internet, Aleo has interwoven zero-knowledge proofs into every facet of their stack, resulting in a vertically integrated Layer 1 blockchain that's unparalleled in its approach. Aleo is ZK by design. Dive into their programming language Leo and see what permissionless development looks like, offering boundless opportunities for developers and innovators to build ZK apps. This is an invitation to be part of a transformational ZK journey. Dive deeper and discover more about Aleo at aleo.org. And now, here's our episode.
So today, we're here with Muthu and Karmit from Ligero, also pronounced Ligero. Muthu is the CTO and soon-to-be CEO of the project. Karmit is the chief scientist. Welcome, both of you, to the show.
Thanks for having us.
It's great being here.
We also have Kobe as the co-host for this one. Hey, Kobe.
Hello.
Let's start a little bit with the name, because I've just basically shared 2 iterations of the name. I always thought it was Ligero. It's with a G in the middle. So I recently learned it's actually pronounced Ligero. Tell me a little bit about the name of this project. Yeah, and maybe what does it mean?
So, Karmit and I, our backgrounds, we did our PhD in computer science, specifically cryptography, zero-knowledge proofs, and secure multiparty computation. We actually did a lot of theoretical investigations in these protocols. About 7 years back, out of a theoretical project came this zero-knowledge system that we said, hey, let's implement. And I think the convention is you got to give a name. Mm-hmm. And, we were about to submit this paper and I was like, okay, what name should we give? And, one of the features of our system is it's lightweight. Uh-huh. So, I'm a little bit of a Harry Potter fan. So I was like, let's use Leviosa. Okay. It's, featherweight from, yeah. But my co-authors weren't big fans of it. So then I went around looking at every language. What does lightweight translate to? Okay. And when I went to Spanish, it said it was ligero, and then there was LIG for lightweight and ERO for zero. And I was like, okay, this is this is good. But I should tell you, maybe even I don't know how to pronounce this well. I have a colleague, I don't know if you know, Daniel Benaro. He knows yes. Spanish, and he corrects me how to say ligero properly.
Nice. Cool. That's a great backstory to the name of this project. So when I saw it, I actually thought maybe for a second it was Esperanto. Now I kind of want to go look it up. But anyway.
Yeah, because we used to do it in Cello.
Oh, yeah. Plumo, right?
Exactly.
Nice. Okay, so yeah, you shared a little bit about like the history very briefly, but I think it would be great to get to know both of you. Muthu, let's start with you. Tell us a little bit about your background leading up to this and why you work on these problems.
Sure. The passion for cryptography, of course, started when I was an undergrad with my undergraduate advisor. But when I started grad school, actually, I was going to do database systems. But then I went to database privacy, and I published a paper called L Diversity, which not many people know, but among all my papers, that has the most citations for some reason. But then from there, I knew like what I wanted to do was cryptography. Once you learn zero knowledge proofs and secure multi-party computation, you just fall in love with it. And of course, I was very theoretically motivated in understanding this. And when I say theoretically, it's about, hey, like, what is the minimal assumptions? Like, what's the round complexity? It's, I'd say much of the initial works that I published, they are not practically feasible. It's actually more about understanding, can a particular security or security feature be achieved? But then out of one of these projects, we had to design something. And, often in theory, we say, hey, if we put this guardrail, there is a chance that it'll be concretely efficient, which is called a black box construction. We ended up doing it and came out a zero knowledge system. And we are like, okay, I had a student who was interested in implementing it. My PhD student, Scott Ames, he implemented it and it turned out to be fast. And at that time, there was only the Zcash crypto system. And our work actually precedes SNARKs.
Interesting.
So
what year is this then? What are we talking?
2000. It got published in 2017, but much of the work was in 2016. So we are actually one of the first transparent ZK-SNARK, although I should say we are not a fully SNARK because it's sublinear as opposed to succinct. Like we can talk about this later. But then after that, I was like, okay, the co-authors like me, Karmeet, and Yuval Ishai, he's a professor at Technion University, we're like, should we commercialize this? And I just put the invention in, I was back at University of Rochester, a professor there. They had a tech transfer department. And, they put me in touch with our other co-founders, our business co-founders, Scott Catlin and Matt DiBiase. Now, what motivated us to start a company? I mean, a little bit, I'll say that we are definitely, excited about this technology and like scaling this technology, but also we wanted real world applications. Like we want the world to see what these primitives can do. And I should just a side note, among all the things, don't ask me what cryptocurrency to buy, but I love blockchains, right? I think the number of people excited about zero knowledge proofs and also more generally cryptography is just amazing. And I think it's a large part due to the blockchain community. But anyways, when we started this company, we were looking for applications in zero knowledge and multi-party computation. We were looking for applications in finance. And, our business co-founders, they're from, Wall Street and have deep connections. We were looking at both on-chain and off-chain, TradFi as well as crypto applications. We looked at multi-party computation more than zero knowledge, actually, when we started. And, we actually have a scalable auction technology for dot pool auctions and a couple of more products that, if it's relevant, I can share later. But along the way, the last 4 years, we also secured a DARPA contract to scale zero knowledge. And, we refined the Ligero system. And right now, I think it's in an iteration that really, I think, can change the space. And we needed a name for the new version, so we call it Ligetron, which I'll tell more later, but I will...
Would you also pronounce that Ligetron?
No.
I'm not going to say that right.
No.
Okay, that's Ligetron. Okay.
I just hope Michael Bay doesn't come and, say that I shouldn't use Ligetron.
That's exactly my excuse why I should say Ligero. Ligero and Ligetron.
All right. Karmeet, let's hear a little bit about your background and what led you to work on this stuff.
Okay, so I have slightly different story. I did my bachelor and my master at Bioline University, and but not in crypto. And then I took a course by back then it was Amir Ellsberg who gave the course on cryptography, and I was fascinated by this area. And I decided that I want to do my PhD in crypto, but there weren't anyone who can actually advise me because Amir was full. And then he told me, there's there's a new faculty member just came to Bar-Ilan, and let's go and you can meet him. And that was Yehuda Lindell.
Yehuda was one of the co-founders of Unbound that got acquired by Coinbase.
Yes. This is with Nigel, right?
With Nigel.
By the way, Nigel also had encouraged that I bring you on this show. So shout out, Nigel, for another recommendation. Anyway.
Absolutely.
Cool.
So I went into Yehuda's office, and he asked me about crypto, and he told me he's working on a relatively new area called secure computation, and started explaining me that. And at the time, it sounded like really far-fetched. Who is going to work on protocols? How useful can they be? But I decided that I like it, and we started working. And I think I worked on the phrase practical secure computation before anyone actually thought that could be even practical.
What year is this, roughly?
Well, so I can tell you a fun fact. I started, when I entered Yehuda's office, I was pregnant with my elder daughter. And I gave birth soon after, and she's over 19 today.
Okay. Wow, that's a great way to know the timing.
Nice.
Yeah. So almost for 2 decades, I've been working on secure computation. And we started looking into the practicality of these protocols before people even thought it could be made practical. Our papers got rejected from conferences, and people just dismissed our papers saying, no, this could never be practical.
Little did they know, right?
Yes, I think one of my papers that actually got published later on during my postdoc in Denmark was about distributed RSA. I think it got rejected over 5 times. People didn't like the paper. They said, no one cares about that. It will never be, I didn't say will never, but it will not be useful. Today, I think many people are implementing such systems. People definitely care, and it is highly cited.
Nice.
So I did my PhD with Yehuda. It was great. It was a great mentor. Then we moved to Denmark for my postdoc, and I had the chance to meet I think the mentor in practical secure computation, Ivan Damgaard, was back at the time, they were the first to implement secure computation with the sugar bit auctions.
Yeah.
Oh, yes.
And it was a great experience. And then came back to Bar-Ilan into a different faculty. And I guess a decade ago, I met Mutu. I mean, we knew each other from before because I was a small community, definitely back then, but we never had a chance to collaborate. And actually, I think we met that time in Denmark, right? In one of the TP MPC.
We actually met once before, but that's okay. I remember that.
But I'm talking about the meeting where we started collaborating.
Yes, that is true.
And I think the rest is history. Right? We became very close collaborators, very close friends. Yeah, we've been doing a lot of great stuff since then.
Then I want to kind of throw it back to the name because I feel like I've been hearing about this project since 2017, but maybe that's wrong. Like when did this first, you kind of hinted there, Mutu, that it might be more like 2020 when something was founded, but when does the first work come out? When do we first see this name and when is the company founded?
Great. So our work got published at ACM CCS 2017. Okay. And in 2018 is when we started talking to our business co-founders and we incorporated in 2018.
Okay.
And we closed our seed round early 2019.
All right. I feel like I've seen the name, I've heard the name for a long time. For me, it was like somewhat under the radar until recently. What were you working on early on? Has that changed?
That's actually a great question. I think one of the things, if we look back in the last 4 years, is we weren't as much promotional, like in terms of what we had accomplished. We were focusing on projects, scaling our technology more than advertising. Not that, we shouldn't, but I do think that's one thing I would say, looking back in the last 4 years. One thing regarding our company is we did have a more heavy focus on MPC or multi-party computation compared to zero knowledge. Although our zero knowledge was being developed in parallel under the DARPA project to scale. DARPA funds fundamental research, and it was great to, we didn't have to raise capital because that was great funding for us to develop our technology. But our focus was on multi-party computation and banks, we talked to the big banks in Wall Street, JP Morgan, Fidelity, Citigroup, etc. And we wanted to build the auction technology. And in parallel, there is also this project that we took for doing the distributed RSA generation for the Ethereum Foundation. Actually, this is one of the first publications that came out of after the company was formed. I'll just tell maybe 1 minute about this project. It was the first multi-party computation project that we demonstrated could run among 10,000 parties. We had envisioned that, everyone maintaining either the Bitcoin or the main nodes maintaining Ethereum could run this protocol. And at that time, this was, people were looking at it for what is called verifiable delay functions. We were able to scale this to 10,000 parties. I think our goal really was to take ZK and MPC and to scale it. And following this, we refined our technology for auctions. And let me just tell a minute about auctions. So, in auctions, you have a bunch of people who want to, bid on a product. And usually it happens with a third party. A third party collects your bids and, announces the winner. But using MPC, you can eliminate the third party. You can just talk to the people bidding, and at the end, only the winner gets announced. Now, this is very useful because it, reduces the information leakage to the bare minimum. Only the winner of the auction is released. And we took this as a challenge, and we actually have this product. If anyone's interested, we can demo this. We can actually scale auctions. For example, imagine you take all assets in the US and all assets in some other market. Let's say that they're 10,000 stock symbols. We can run an auction in parallel for all these 10,000 symbols and complete it in 5 minutes. This is, again,
that's really good.
One of the challenges we took, and we were able to deliver. Now, while we are talking about MPC, at least I'll say how people think about MPC today was different from at least 2 or 3 years back. Because when we went and talked to people about it, they were like, MPC, is that zero knowledge? And I had to control my anger inside, but also at the same time, I think
it falls under the royal ZK sometimes.
I mean, the hot topic on crypto Twitter now is MPC also threshold signatures? But yeah.
I know. Oh, no, please don't get me started on that also. But we didn't realize that there is sort of an education problem. Blockchain has done great for zero knowledge, but not yet for MPC. And so we created a cute little product, which is also available, which is to schedule meetings. Now, you can imagine this is a very basic task, and you want privacy. I don't want to tell what appointments I have. Even if I don't show what the appointments are, I don't want to tell when I am free and busy. But you can use MPC to find a common meeting time.
What's that called? Do you have it?
Meshcal, MESHCAL, meshcal.com. Mesh and calendar.
You have some good names that are hard to pronounce there. But anywho.
But, then came the zero knowledge proof. And then, I think we have now, I would say, a little bit pivoted to exploring what the zero knowledge is going to do to the space. All these other projects are still there. We have, demos for all of them, if anyone's interested.
I can add, during all these years, we had 2 jobs. Our main job was we had academic positions, which are really, really intense by themselves. And in parallel, we've been trying to run the company. This is part of why we've been slightly under the radar. And also, as a scientist, I think we really cared about spreading the word about this technology. The place where we come from, we really value privacy. We really think of it as an important value in society. We really think society can benefit a lot from understanding why privacy is important. And our goal, our mission was to make MPC, also now zero knowledge, as a tool that people will really value and appreciate and would want to use it because they will understand that it's for their own benefit. And I think privacy is something that we should educate for. For instance, when I give many talks in high schools in Israel, I mean, people invite me for science days and so on. And I speak about crypto, but every time I finish my talk with, I have this slide on explaining about privacy and why is it important. And I mean, you can see that it's missing. And this is something that we should definitely educate more. I think this is our mission as scientists.
So first of all, I completely agree with you, Karmit, about that point. And especially, I think a lot of people are not realizing that they could have this kind of non-financial privacy in their lives, and they take it as a given, which is not that good. Yeah, and Mutu, to your point, I think that I also get why you had to do MPC stuff for a few years if you were working with TradFi people, because I think that ZK really flourishes in this kind of crypto space because there are very strict trust requirements which don't necessarily exist outside. So I kind of get it.
I want to just quickly return to what you were saying about like your first contract being with DARPA. What's it like working with them? Can you say anything?
So there are different kinds of projects, but this project comes under a category of fundamental research. I think they really want to promote the technology. Like this is clear from their intentions. The way DARPA works is actually, we had an excellent program manager. His name is Josh Barron. And, he finished his term, and then we have another excellent person his name is Dan Balak. But they said, look, we need to scale zero knowledge. They kept metrics, and we actually beat the metrics like halfway through the program in terms of how they wanted to scale. With DARPA, the only thing is whenever you announce something publicly or publish, you just have to get sort of an approval from them. But this has never been sort of a bottleneck in terms of getting this technology out. But
cool.
I think it's a really great program.
You're allowed to publish it. Can you open source the work you do with them?
Yes, you can do everything. Yeah, you just need to get their permission, which again, I think this research is not too sensitive in that sense.
Got it.
I think it was a great experience also collaborating with many groups, seeing the results of many different systems. I think it really pushed this project.
Okay, so let's talk about Ligero itself. So the construction and the paper, it had a bit of a history, right? It's based on earlier works like MPC in the head. And so how does that lineage look like?
Let me give you a little bit of a background on MPC in the head, which to my mind, I think it was one of the most brilliant papers. So,
and it's not an MPC protocol.
Oh, it's not?
Not exactly. I will explain. So the starting point is a paper by 4 authors, Ishai, Kushilevitz, Ostrovsky, and Sahai from 2007. They came up with a new technique to design zero-knowledge proofs. Now, let me tell you that as cryptographers, we care about the complexity class for which we can design zero-knowledge. Specifically in crypto, we care about NP problems. And this class is the set of problems where you can validate or verify efficiently. Now, classical results on zero knowledge showed how to build zero knowledge protocols for this class by basically focusing on a class that is considered more difficult within this class. These problems are called NP complete problems. So like satisfiability. So if you build a zero-knowledge protocol for this problem, then you basically cover the entire set of NP problems. Now, the ICOS paper, I'm going to denote it ICOS by the initials of the authors. So this paper, what they showed, first of all, they took a detour from the original way or the classic approach of designing zero-knowledge proofs for NP-complete problems and basically build directly a zero-knowledge protocol for every NP problem. And the way they did it is basically instead of using reductions like you had to do if you wanted to work with NP-complete, they pushed the computational task into building or using an MPC protocol by the prover. Now, maybe it's a good time to distinct between zero knowledge and MPC, because that was going back to the discussion we had before. MPC is a generalization of zero knowledge, right? In zero knowledge, we have two parties, the prover and the verifier. In MPC, we can have an arbitrary number of parties. In zero knowledge, only the prover has a secret input. In MPC, basically each party can have a secret input. Mm-hmm. And also the functionality, right? In zero knowledge, the prover is convincing the verifier by the validity of some statement. Yeah. In MPC, we could just compute an arbitrary function. Now, why do I mention that? Because MPC is general enough to have different flavors of security definitions or adversarial models. And looking ahead, this what gives this MPC and the head technique its flexibility, because it can be instantiated with different protocols. Now, going back to MPC and the head, what ICOS basically did is the following. They said, let's define a function or a functionality. In this functionality, take the secret input and secret share it among a set of parties. Now, the prover is going to virtually, right? This is where it comes in its head. The prover is going to take some protocol and emulate this protocol in its mind, in its head, computing a function that basically validates the witness. Now, when you run a protocol, you have a transcript or the messages exchanged between the parties and views. A view is basically the secret internal state of a party and incoming messages. So now after virtually running this protocol, the prover is going to take all these views generated by the virtual parties and commit to those views. And this is the first message of the MPC and the head protocol. Now, after committing to these views, the verifier is going to challenge the prover to reveal a subset of these views, for which it's going to check for consistency. So what does it mean? It means that if, for instance, one party sends a particular message, so it should appear in the view of the other party. This is what they call pairwise consistency. And what ICOS showed is that if you have this pairwise or local consistency, you can prove that you have also global consistency, meaning that if every pair of views are consistent, that means that the statement could be correctly validated. So this is the core idea of MPC in the head. And it was also implemented, for instance, by the ZK-Boo paper. Yeah. I think it was implemented and already demonstrated to be practical. However, the basic approach is that you get a constant soundness. So you really need to repeat the protocol multiple times if you want to get really small soundness. And this is where, for instance, Ligero kicks in. Because if you enhance the properties, the security properties of the MPC protocol you're actually using, the virtual protocol, then you can get much better. All the properties that Ligero has, like going into sublinear and so on.
Something that I remember about MPC in the head and ZK-Boo is that because if you want to enhance soundness, you have to repeat, like you said, is that you can run a lot of these in parallel and gain efficiency in that way. Is that also true for Ligero?
So we won't have to do that because by choosing the right MPC, you won't have to repeat it in parallel. And also, there is a difference between how Ligero works to other systems. Like, for example, in Ligero, it's not that you need to use large field sizes to get good security, which happens in other systems where the security is related to 1 over the size of the underlying field.
Yeah, for SNARKs, it's very required. Yeah.
Yes. But in Ligero, actually, there is a different mechanism that you can repeat what we call like code test and linear test as part of it, even if you have a small field and get it. Now, repeating in parallel, this one needs to be careful. And I actually listened to Justin's podcast last week where he talked about parallel repetition of these things. And I just want to point out, he mentioned that he blew away two researchers by saying it, and one of it was me. So I'm just revealing the identity of
Nice.
one of them. So, I mean, you want to be careful for the ZKBoo setting. Repeating in parallel is fine because it's actually 1 round of interaction with the verifier. Ligero is like 3 rounds of interaction. And when you parallelize, you're not going to get the best parameters. So you would rather do it in the MPC itself. But maybe I'll just tell a little bit about this MPC in the head from, how it is today. One of the things also for Karmeet and me, in this thing was that we came from, I want to say a little bit from the cryptography world as opposed to the complexity world. For me, like the works like Elie Ben-Sasson and so forth, like they come from this complexity world of doing probabilistically checkable proofs and which has evolved into interactive oracle proofs, as well as, the kind that's based on the Sumcheck protocol, which also is from the complexity world. But we started from the MPC world, but actually now you can unify it. Everything is an interactive oracle proof. In what Karmeet described, it's about committing to views of these players. You can think of this as an oracle proof. Like these views are being put in an oracle and the verifier is opening a few of them to check it. Now, the difference between, again, the complexity world and the cryptography world here is actually the size of the symbol in the oracle. Now, in the complexity world, including even SNARKs, when the verifier queries one of these oracle entries, it's a single field element typically. And because this is how the complexity world has optimized probabilistically checkable proofs. They care about getting the symbol size to small, even Boolean. But in the MPC world, we don't care about it. Like the view of a party, which is one symbol, can have a lot. And what we've found is that this actually helps us leverage things better than the complexity world, but also more from a concrete efficiency and a usability standpoint. But I want to say that MPC in the head can be viewed actually as an instantiation of an interactive oracle proof.
Interesting. I want to just highlight, it's funny because I think you're the second group to talk about MPC as sort of the meta, the higher kind of distinguishing factor, and ZK living underneath it. We on the ZK land think of the Royal ZK, which is just the umbrella term that VCs use to describe all advanced cryptography. But I'm sort of left, after what you just said, a bit confused about exactly what this is then. Is it an MPC protocol? Is it a ZK? Is it a weird new combination of the two? Like, how do you define this? It sounds like you're coming more from the MPC land, but yeah, I'm just curious.
So this is exactly what I wanted to add. So as a PhD student in crypto, or every PhD student studies like one of the most classical results in MPC, how to compile passive to active protocols. You start with a protocol with very benign security properties, and you use zero knowledge to compile it into a protocol that is, let's say, much more secure or secure against stronger attacks. And this is actually the very first application of zero knowledge proofs. And it is called the GMW compiler. Very, very famous results and fundamental in cryptography. Now, what ICOs showed is basically the other direction. So they showed how to use actively secure protocols to build zero knowledge. So thinking out of the box, because up until their paper, we thought of MPC as a generalization of zero knowledge. And we knew that zero knowledge can help to get better MPC protocols. And they actually showed the other direction.
Let me add one thing to this. And Anna, actually, this confusion makes sense to me because if you look at these two objects, right? as Karmeet said, multi-party computation is a generalization of zero knowledge. It's in fact more powerful, and in the most sort of general form, it actually demands more. And let me explain what this is. For zero knowledge proofs, including the Ligero system, you just need hash functions, just like SNARKs. You don't need any what we call public key primitives, elliptic curves or like lattices or anything. We don't need public key objects for building a zero knowledge system. But for multi-party computation, this is necessary. You need something called an oblivious transfer. That's one of the minimal objects that you need. And these can be based only on public key assumptions. Actually, there are separation results that say hash functions are not enough. So when we are using MPC in the head, this begs the question, hey, like I'm using an MPC protocol. Does it mean now my zero knowledge needs these public key primitives? And the answer is no.
Okay.
And the point is that there are several variants of multi-party computation, and the variant we are using is something called an honest majority multi-party computation, which means that you actually can build these without any cryptographic primitives. And it is those multi-party computation protocols that we plug into this compiler to get a zero-knowledge system based on hash functions. So maybe to answer your question, it is a zero-knowledge system, like in the sense that it needs only hash functions, but the techniques that go into it has come from the MPC world.
Okay. Is it a ZK system then?
It is. Actually, this is one of the things, maybe I want to say that whatever we have designed, like by default, they are zero knowledge. And I kind of want to like compare it with like sometimes the other systems, even like Sumcheck protocols. Just when you use it, like on the face of it, they need not be zero knowledge. In fact, Jolt is not a ZK VM. As Justin says, it needs to be called a succinct VM.
Oh, wow. Okay. Yeah. It's not ZK.
But the Ligero system is zero knowledge by default. And this is something you get for free because you do MPC. Because MPC, has the privacy already in it. So you get it baked in.
So what were Ligero's improvements above MPC in the head and other works that made it, a new work?
So Karmeet mentioned this work, ZK-Boo. In fact, it was the first work. We were really, we really loved this work. It appeared in Usenix. It actually got the best paper at Usenix for implementing this MPC in the head.
Oh,
and
cool.
Let me say that line of work is still active today, and it is leading to post-quantum signatures. We are not involved in that, but I want to say just give a shout out to MPC in the head for, post-quantum digital signatures. But to compare that kind of MPC in the head to what Ligero does is that here is a challenge with MPC. Typically in MPC protocols, as Karmeet said, there are these views that I said, hey, you can think of it as an oracle proof that you put in an oracle entry. But the size of these views are proportional to the size of the computation. Standard protocols of MPC, this is the case. Yeah. Now, this is what ZK-Boo did. If you use this, your proof lengths are not going to be short. They are going to be the size of the computation. But when you want to build SNARKs, you want to put things on chain, you want this to be succinct or sublinear. So you want to devise an MPC protocol where the size of the view of each of these parties in your head needs to be smaller than the computation. And here there is again a work of, Franklin and Young back in the 90s. They introduced this concept called packed secret sharing, which said that, standard secret sharing can only share a single secret. But if you play with the thresholds a little bit, you can actually pack a lot of secrets in a single share when you distribute it among parties. And this also led to multi-party computation protocol with exactly this feature. So Ligero took advantage and actually you need to sharpen it and tighten it here and there to actually get a concretely efficient. But the first version of Ligero was that. And one of the, again, things about these MPC protocols is they had very simple structure. They used Reed-Solomon encoding for which you have fast algorithms to do it. And as it turns out, Ligero remains as one of the fastest provers even today. And I'll tell you, Ligetron is faster than Ligero, but it still remains as one of the fastest prover time protocols. And, even if you look at papers today, they still compare back to the 2017 numbers. We just didn't publish more faster numbers, but they still compare with the numbers that we published in 2017. But Kobe, to answer, I'm only talking about Ligero. Ligetron has a lot more features, which, I can talk about. But Ligero is, as a protocol, it's hash-based. It's not a snark completely because it's not sublinear. The complexity, the proof length is square root in the circuit size as opposed to polylogarithmic, which is what people typically associate with snarks. But the second thing is also that the verification is not is not succinct. But this is not, again, I want to say it's not a bad or a good feature. In fact, all zero-knowledge systems, the verifier needs to spend time proportional to the circuit. It is just that when you repeat it many, many times, you can do some optimizations. But if I tell you I want to prove a single statement once, the verifier at least has to read the statement. Otherwise, it doesn't know what it is being convinced. But in any case, the verification is also, it's not succinct. It can be when the computation is structured, which is what is the case in terms of machine learning applications or roll-ups and so forth. The computation is highly structured. When it's highly structured, Ligero is both sublinear in proof, but also the verification is succinct.
Yeah. So why do you think it hasn't received so much attention like, other SNARKs protocols like Growth 16, Plonk, and Starks? I have my guess, but I'm curious what you think.
Okay, I wasn't prepared for that question. Okay, so let me try to be as less or as much controversial. Now, even after building a system, I think it takes engineering. It takes also applications. It also takes, I should admit, some business savviness to bring in the forefront. Now, maybe just comparing it with SNARKs. Also, maybe one more sentence I'll say here because I listened to Justin's podcast. Maybe, someone needs to be quixotic and like, hey, go for MPC in the head like he goes for Sumcheck. But maybe we'll do that.
Is that you? Okay.
I mean, in all, it's hash-based. It's post-quantum secure, just like SNARKs are post-quantum secure. In fact, SNARKs scale polylogarithmic while Ligero scales square root. But for up to a medium-sized circuit, actually square root beats polylog. And this is one of the misconceptions also that Justin had actually written about comparing Ligero and SNARK proof lengths. I didn't answer your question, Kobe, but maybe the answer to your question, it's more that we didn't find the right application until now for showcasing this technology. And let me also say that we have applied our zero-knowledge technology in the MPC world. And this goes to also, Anna, like maybe just your question before. I had just one sentence to add to what Karmit said. There is a symbiosis between MPC and zero-knowledge, right? MPC is more general than zero-knowledge, but the techniques-wise, they have gone from one to the other and back. Right. So in that sense, we have actually employed zero knowledge quite a bit. In fact, our first RSA project, as well as in our auction project, we have used the zero knowledge insights that we gained in Ligero back in MPC. Yeah, actually, and maybe one thing tying back to the name of the company, I didn't get to name this, our original work, Leviosa, but the following work on MPC, there is a work on MPC with Karmit, me, Yuval, that we named it Leviosa.
Okay, that does exist in the world.
Yes.
Cool.
Yeah, I guess I'll add my guess. Again, going back to Justin, which is the hidden participant in this episode as well.
He's just right across here in Georgetown.
Yeah, exactly. So one point that he made in his recent post was that as a community, at least in the crypto space, we've been very, very focused on optimizing verification time and, on-chain verification and so on. And like you said, people still compare proving times with your 2017 paper. And now there are other use cases and other applications where proving times are much more important. And, you'll deal with verification times in other ways. So I think that's one of my guesses, at least.
This is absolutely right. One of the hidden things that a lot of the ZK system, maybe this is the controversial point, is that they hide what are the prover resources that are spent in building their products. And I think for systems like rollups and so forth, I think this investment pays out. Like, you can push those costs back down to to your users. But in many scenarios, this cannot be the case. And focusing on prover time is important in these settings. Like, I mean, we are looking at client-side proving with our technology, as well as proving very large-scale computations frequently, like, machine learning inference. And here, prover time is going to be important. And let me just say, I would not say prover time. I actually would say prover resources, because that's different.
Yeah, that's true.
So you have teased Ligetron already in this episode. What is this? I'm assuming it uses things that Ligero has in it, or is it a new proving system, or is it a new construction? Yeah, tell us what it is.
So I want to think of Ligetron as Ligero 2.0.
Okay.
And really, Ligetron follows the blueprint of Ligero, but differs in two key aspects. One is that it is memory efficient. In fact, I would say that it is the only zero-knowledge system that is concretely efficient, that is memory efficient without using techniques like recursive composition and incrementally verifiable computation. So it's, as it is, a memory efficient zero-knowledge system. And the second key factor is that, key differentiator, is that it can consume WebAssembly programs as input. In that sense, it's almost a ZK-WASM. I can tell you where it isn't, and how we are making it a ZK-WASM or a ZK-VM, but it can take as input a WebAssembly as a program as an input. And one more thing I just want to kind of tell about this is that it's also, maybe this might change it, ZK advances come, pretty fast. But I want to say today, it stands as the only one that can run completely from your browser. So we actually have this, like if you go to ligetron.com, you can put a C, C++, or Rust program. Well, right now only C or C++, Rust is not integrated, and compile it to WebAssembly, and you can run the entire computation from your browser. We have tested it up to 1 billion gates. It takes 10 minutes or 20 minutes on the browser to go to that scale, but it will run. And the memory required by the zero-knowledge system is closely or proportional to the memory required by the underlying WebAssembly program.
Understood.
Yeah, and that's pretty impressive because it's also fast for 1 billion gates.
Yeah.
But also a lot of other systems almost inherently require you to have all of this in memory at the same time, or at least in some level. So yeah, that's pretty cool. It's pretty unique.
The current technology, again, I'm not going to say that, look, like we observed the memory bottleneck a couple of years ahead, or at least, before the blockchain community did with their rollups, because we had to do for DARPA, they wanted to scale trillions of gates on commodity hardware, right? Like they didn't want heavy hardware, but they wanted to go up to trillions of gates. So we had to solve the memory bottleneck. I want to say that this DARPA program, we are actually part of a group with Stealth Software Technologies, is another MPC company. There are other groups as well that participated. I bring this up because almost all of them did not work on a SNARK. They all worked on what are called VOLE-based zero knowledge, which is an interactive kind. They're not blockchain ready as is, like you got to massage it, but it is not meant for blockchains in some sense.
Like it's not publicly verifiable.
It's not publicly verifiable.
Yeah.
I mean, there are new works that are trying to do it, but as is, it is not publicly verifiable. But we focused on SNARKs. And I want to say for the VOLE based, that's actually more close to being an MPC. It uses public key assumptions and so forth, but they get memory efficiency a different way. But in the SNARK scenario, I think either we were lucky or so forth. We encountered this problem and we tried to solve it. And I want to say that as part of our mission, we want to make it easy to use the system. I'll say that, I've, again, not pointing fingers or naming names, I've tried downloading all these open source repositories, and I did quite a bit of coding as an undergrad, but, let's say that my skills aren't. But our top engineers have taken hours to compile and use this. Right? Like there is still like a significant learning curve to start using this technology. And I'll say like our browser implementation, like anyone write a simple C program, you can do it from a browser today. And this is one of the things that we want to keep in mind as we are evolving. Like we still, I think bringing Web 2 to Web 3, which is something that we feel like strongly about, like I think this is going to be important. You want to make things that people are familiar with Web 2 so that, bringing development here it's easy.
When you talk about memory efficient, I actually don't really understand what the memory is there. Can you describe that? And it sounds like there are other techniques to create this memory efficiency, like recursion you kind of highlighted. But yeah, what does memory efficient actually mean here?
The current zero-knowledge systems, the way, or the SNARKs, let me just be specific so that I don't bring other techniques in. You have to first run the computation and you observe all the intermediate values of these computation. And really the modern ZK-SNARKs, what they try to prove is that every intermediate computation was performed correctly. Now, the way they do it to get succinctness is you need to do some kind of mixing in terms of checking these constraints. This is where all the error correcting codes, all these things like, polynomial evaluations help you in sort of mixing the constraints in terms of checking it. Now, one of the things that modern SNARKs need to do is when they run a computation, they have to take all these intermediate computations and have it in your head. Or you need memory proportional to, like, imagine that I expanded it out as a circuit, I have wire values, I have to put all of this in memory. And then after that, apply certain cryptographic techniques on top of this. So in this sense, when I say memory efficient, the memory I need is proportional to the entire computation, as opposed to, but when you run your program, you have when you run your program on your CPU or anything, like it does not need to keep past values, right? Like, I only keep what is in my registers and a little bit in my memory. But as I do the computation, I don't need to keep the past values in memory.
Okay.
Now, when I say Ligero is memory efficient, it can also do garbage collection. This is what I mean. Like in modern computers, you don't want to waste memory. As you do computation, there is something called garbage collection that removes all unused stuff.
Okay.
Now, modern ZK-SNARKs, or at least what the last 2 years, what people are trying, how they are trying to address this is something called continuations, or like recursive composition is one example where you take your entire computation, you break it into chunks, and you prove each chunk separately, and then you combine these proofs using a second layer of proofs. And you can do this multiple times. You can have like a tree-like structure and you can do it. Now, this is memory efficient in that each chunk or shard can be, you just need to choose the size for which you have memory. So then after you've done that proof, you can move to the next shard. But this is not actually how people do this, because if you really did this, you'll run forever because you're going to do the first chunk, then the second, you'll do sequentially. This is going to take a lot of time. In fact, for example, StarkNet, what they do is they have 200 computers that does this in parallel. And then they do recursive composition. So one thing that I want to kind of highlight here is back to my point about prover resources. These techniques of recursive composition and incrementally verifiable computation can get memory efficiency, but at the price of very heavy hardware. But Ligero, on the other hand, we can get this memory efficiency on standard hardware. And if you throw in more hardware, you can leverage parallelism, but on standard hardware, you can already get this memory efficiency.
So when you talk about WebAssembly and Ligetron, it's one instantiation of how to use Ligetron, right? Is building a specific ZK VM for Boson. And I guess my question is it especially useful to use Ligetron or Ligero for ZK VMs, or you see other, let's say, specific instantiations for other applications like ZKML or other kind of things?
Actually, your former question sounds to me more like a business answer, and the latter is a little more technical, but I'll try to address both these questions. For the ZK VM itself, I mentioned that we are almost a ZK VM. So where are we not a ZK VM is that we can only take programs that have what I call oblivious control flow, meaning that I cannot have an if-then-else in the program where I branch on a secret value, because the verifier needs to know really exactly how you flow through the program. We have a couple of papers in recent, the last year and this year that show how we can remove this, which is in the pipeline to make it a full-fledged ZK WASM. And it is different from how RISC-0, SP1 and Jolt are doing it. They have this fetch, decode, execute cycle for every instruction to solve this problem. for us, we're going to solve it differently. That's going to give us a lot more mileage. Instead of fetching instructions at a time, we can fetch blocks at a time. So this amortizes the fetch decode over a block as opposed to per instruction. So we hope to get much more mileage from making it a ZK-WASM. But in terms of, okay, are we going to build this? Now, I think the way, at least I'll say it's all a little bit in flux, but we want to think more about where this technology is going to be useful. We want to think about products. There's no doubt we're going to improve our ZK tech. Right? Like it's going to, like, we want to make it faster. We want to still keep the memory efficiency. We want it to still be easy to, code applications, but we want to think of applications. And the two domains we are looking at, one is enterprise, where we are looking for client side proving for transaction level privacy for tokenization. And on the other end, we are on the crypto side, we are looking for verifying AI computations. And I just want to maybe mention one benchmark in the AI computation space and how it ties back to WebAssembly, which is one of the questions, Kobe, you asked, is that Modulus Labs recently made an announcement a couple of months back where they were able to verify, actually the first that verified the GPT-2 inference on chain. Yeah, really.
Very impressive.
Very impressive. And so we, in collaboration with NIM Network, we said, okay, let's also benchmark. Now, our proofs can't go on chain yet, which is, I want to just point in comparison to Modulus Labs. But what we wanted to really do is we wanted to make it easy to do this. So we really took a pure C program. It was called there was one of these GitHub repository by Karpathy or someone who did for the Llama 7 billion model, which is 5 times bigger than the GPT-2 XL model. And we just compiled it to WebAssembly and ran it. We did no optimizations, no lookups, no nothing. Like we just ran it through our system. And it came out in 14 hours, which was sort of like a 60x improvement. But if you look at the hardware, we were like 100x better hardware than Modulus Labs. So just coming back, I think, okay, between WebAssembly and, say, RISC-V, there is a question, and I can spend a whole hour why WebAssembly is better. But the long story is that WebAssembly is more versatile. And we picked that for that reason, but there is no reason to keep that. Like we can really do any VM that we choose. But WebAssembly has some very nice features that we can take, garbage collection being one of them.
Yeah, and like, do you specifically like VMs because it's highly structured?
Easy to deploy, like easy for people to write applications. That was really, our motivation was to get a good intermediate representation. Rather than using R1CS or like these specific circuits that have, a learning curve, we wanted to pick one that's easy.
Okay. And maybe, like you said, the elephant in the room, it's not on-chain verifiable yet, but how optimistic are you that it could be made?
I won't use the word optimistic here. I'll say that, no, we are going to get the proofs on-chain. There are two steps specifically that we have to do. The first step is we have to go to what is called the pre-processing variant of this. This is the kind where I said, like, hey, I want to prove something, but I'm going to prove this over and over, which means now I can give a small amount of like a hint or information for the verifier that can verify these computations over and over again. So this is still, we have the research written, internally, we know how to make Ligero pre-processing. This is required because we have to reduce the verification size. Yeah. Now, our estimates say that from proving a statement to verifying its proof, there is a 50x reduction. So just to give numbers, let's say that I start with a 200 billion gate circuit, which was what the Llama 7 billion model, like if I get a 50x or a 100x improvement, it reduces to 2 billion or like 4 billion. Mm-hmm. I can recurse it one more time and I can make it like 100 million. And now I can put anything if you want into prover networks, deepens, anything, like you can just push it and like we can get it on chain. We are not looking to optimize. We will do the research, but it'll be easier for us to just plug into some other system to finally bring this. Once it becomes a manageable size, we could just plug into the system. One point I want to mention here is that being ZK by default actually helps here because we don't need to worry about the composition giving us privacy. If you start with a SNARK as opposed to a ZK-SNARK, when you compose it, which you have to bring proofs on chain for many of these systems, you want a zero knowledge system, but are you going to trust some other service to do that? But for us, we don't care because the first step is zero knowledge. We can push it in any network because The second step, you only need a snark. Privacy comes already in the first step.
At what stage is the project? So at Ligetron specifically, like you've announced it, but are you building it? How far along are you with that?
Ligetron assets, I mean, this is fully functional. People can start using this with the caveat that you need sort of oblivious control flow on your C program. But where we are going with it actually is we are right now aligning design partners to really build some products in the space to educate us how to evolve the ZK infrastructure. And we are starting with, I mean, we are close to having two partners, one in the enterprise space, with our Wall Street connections, where we want to use ZK for transaction level privacy for tokenization. And this is going to require things like anonymousZether andZether that they want, but with KYC AML. In this sense, we are different from like Aztec and Zcash that don't have that in their or at least in their immediate goals. We want to do it like we want to be regulatory compliant and so forth. So we are going to enhance our browser-based ZK for these applications that require client-side probing. And on the other end of the spectrum, on the crypto side, we did this Llama 7 billion inference. We are thinking about how to build the next infrastructure for AI. And, we are looking to collaborate with this NIM network for bringing AI gaming on chain. Both of these, in some sense, I mean, the first step for us is to bring the proofs on chain. As Kobe said, that is kind of one of the biggest milestones, which I think we should. I mean, my estimate is like 2 to 3 months. We should be able to bring the proofs on chain. But the way I think about it is like we're going to have like some design partners to build certain products, but on the same end, we want to build a unified ZK that's going to help everything, right? So, because when we bring a unified ZK, what we're really unifying is the developing tools more than the underlying ZK.
Now, what about the future research work? Like, are you actually going to be doing a Ligero 3?
Yes, without a doubt, right? Like, I think... again, one of the things for Karmeet and me that's been like really fantastic working in this is like the amazing research, both from the industry side as well as the academic side, like how ZK has progressed is amazing. And, I'm going to be humble and honest and say it's like, it's not going to, Ligero or Ligetron is not going to remain the best if we don't improve it. Mm-hmm. And I'll say for now, Karmeet and I have 5 improvements down the line, like that we know what to do, but we don't know what new improvements are going to come down this year. That one other thing that I want to point with the MPC in the head is what Karmeet and I have like really sharpened our skills in the last 4 years is we have looked at all the optimizations that go on elsewhere and we know how to bring it back into MPC in the head. So we hope to continue to do that and, stay competitive.
What's the most exciting work that came out recently to you outside of your own?
I'm a little afraid to say this because I haven't done the diligence, but I do think that the works of like Lasso, like of Justin with the lookup arguments, as well as Binius, which is also something that is making its rounds. I know how to bring all the lookup arguments into MPC in the head. I don't know yet how Binius does, but interestingly, the Binius commitment is actually the structure is the Ligero polynomial commitment scheme.
Oh, interesting.
So I hope that that's going to also improve what we build.
Interesting. So I want to say thank you to both of you for coming on the show and sharing with us the story of Ligero or Ligero, the advent of Ligetron, and some of the future work you have planned. Thanks so much.
Thank you. It has been a pleasure. And thank you, Nigel, for making the connection.
For the recommendation.
Yeah, and thanks, Anna, and also actually special thanks to Kobe too, who's also been advising us through the last few months. And thank you. I hope maybe someday I'd like to ask the two of you some questions in some podcasts because I have so many to ask you guys.
Yeah, it was a great conversation. Thank you for sharing all of this.
Cool. All right, I want to say thank you to the podcast team, Rachel, Henrik, and Tanya, and to our listeners. Thanks for listening.